Hi, everyone. Good afternoon, and thanks for coming for the presentation, even though in the brochure there was no mention, no description because of a last-minute change. So thank you. And we're going to be one of the last blocks between you and the beer, so thank you for hanging on. My name is Ameet Chaubal, and I work for Accenture. A part of Accenture is a big data practice, and with me I've a friend of mine, Mauricio, who works for another unit within Accenture called the Labs, where they get to do much cooler, fun things without having to worry about utilization percentage and such mundane items. We're going to talk about Cassandra as the formation of a real-time ingestion system and talk about some of the business use cases that we've come across and how we can improve that and gradually take it to the next level of sophistication. So the presentation, what we're highlighting is one business problem, a use case, where we looked at a very common design or problem pattern and how we could solve that using newer technology, highlight how it has been solved in past maybe 10, 15 years, what are the deficiencies in that, and how the newer system addresses that, and then take it from there and come up with additional issues or opportunities that we have open to ourselves, and what are the technology stacks that are available and how we can leverage those technology products. So the business case is fairly straightforward. You've come across this in many organizations. You have some sort of an e-commerce or web application that is generating huge amount of information at very high velocity. You want to capture that information and store it in some sort of database so you can run queries, perform analysis. You might want to extract the information from that database, put it in a data warehouse for historical analysis and some sort of business intelligence application. Fairly standard, common business use case. So in the olden days, you might have had an e-commerce site. You might have had some sort of a queue to de-link the website from a database. And then from the database, eventually you go into a data warehousing system. Just to add a few more details about this particular problem that we were dealing with, this use case, the messages that were being generated or the events that were being generated are very high speed to the tune of 5,000 messages per second. This website belonged to a financial institution, so it had close to 100 million people using such a system at one point or the other. The size of the message was fairly common, around a kilobyte. Some more information, the queue, of course, allowed us to decouple the user experience from what was happening downstream, such as the transient database into which the data was being stored. It also allowed us to have additional syncs, so we can store the information into flat files for further analysis using other products such as Splunk or R or anything like that. Of course, there was a dedicated storage tier, and then finally a data warehouse where we had business intelligence and historical analyses. So what's the problem with that? Now, the actual information, actual business use case had two sites separated across two data centers 1,000 miles away, and that was done in order to support the volume. Each site had its own queue, and each site had its own transient data storage platform, or RDBMS. The queue had a lot of replication issues because we're talking about separating over a great enough distance and network latency going about 40 to 45 milliseconds. We also had the issue that there was no holistic view of the data. Since the data that was stored in these transient systems was in two separate systems, there was no way to ask a question, what is happening to a particular message, unless you looked into both the databases separately. And finally, because the data was in separate transient databases which needed to be extracted and then finally consolidated and put into a data warehousing system, there was a lot of lag up to about 6 to 8 hours before the information was available in a data warehouse for some business analysis or business intelligence. So the way we, just to recap, again, large amount of information coming in. And of course, in addition to all the problems, there was no way to do real-time or low-latency dashboards where we can show that to the user or plug it into an application. At the same time, there was no pattern detection that we could detect some problem as and when it was happening. The solution that we used was looking at one of the weakest points, which was the transient system, transient RDBMS that was unable to keep up with the incoming load. So the first thing you have is you have the event being generated by the online application, uses some sort of a JMS publisher to get the data into the queue. And from the queue, the information is fetched by consumers, which were deployed across a cluster of WebLogic servers, and then getting the information into the consumers, and then using Hector client, putting the information into a Cassandra system. The Cassandra system from one geographical location was replicated to the other data center, and also additional layer of Hadoop was added, essentially meaning job tracker and task trackers were added that allowed us to do batch processing, MapReduce, or Hive queries, at the same time perform real-time dashboards or low-latency API-based application. So this sort of architecture allowed us to solve some of the basic problems that I had highlighted, which were missing from the original design. Some of the salient features of this solution is the data model in Cassandra. And this is where I wanted to highlight, if you compare this to a relational system, in a relational system, as long as the data exists in some sort of tables, some sort of entity, you can always ask a question and you will get the answer. It might be stored in a third normal form, it might be denormalized, but somehow you are going to be able to query the data. May not be the most optimal form, but you will get the answer. Well, with Cassandra, the sort of questions that you can ask are, to a large extent, predicated upon the model in which the data is stored. So in this case, we had chosen a wide row model where a key has a large amount of columns storing the data in a horizontal fashion. Now, one thing about that to keep in mind is that each row is stored on a single server. So if I have about 5,000 messages coming in per second, at 60 seconds, I'm going to have about 300,000 messages or events that are being generated. All that will go to a single machine, generating hotspots, and one machine is chugging along and working very hard while the rest of the servers in the infrastructure are just sipping tea and not doing anything, which is probably not the best thing to do. So the way we're taking care of this is making the key into a composite structure, where we're adding a fabricated, concocted partition number, which is some multiple of the number of servers, so that the whole row is going to be broken up into chunks. So if I choose a number, let's say 100 partitions, which is what we used, the 300,000 events would be divided by 100 and made into 3,000 events per row, which could be stored by a single server at a given time, and at the same time separating or distributing the load across all the cluster. The other important thing that we looked at was composite columns. So unlike a relational database where the name of the column really doesn't contain any important information, you can ask a question such as select star from employee where social security number equals blah. But you can't say that select star from employee where column name equals S something. Well, in Cassandra, we're able to do that. That means the information can be stored in the name of the column itself, and which is what we made use of in this case. Additionally, the name of the column was made into a composite structure. And if you notice, there is a logic to making the composite structure, which is increasing in granularity. So if you start with a data center, what we're saying is that it has a very low granularity. That means a lot of rows or records will have the same data center value. Within that, we will have a user ID, which will have a certain number of records for that user. Within that, we might have individual messages by time or the actual message. So the granularity of the message is increasing starting from the beginning of the composite structure. And the value of such a column could be anything. And in this case, we're using it for some sort of a status that we can generate to say that we queried this data or we asked some questions so that later on we can be sure that, OK, this part of the record was processed. So it allows us two aspects to, or two different pieces to make use of: the value of the column and the name of the column itself. The other thing is that the row key, in this case, being a minute value, allows us to collect or bunch or group together records in a horizontal fashion for each minute. At the same time, we added another column called hour, which allows us to group in a vertical fashion. So we have two levels of granularity by which we can ask a question. One is by minute, and one is by hour. And the one in hour in a vertical fashion is essentially using a secondary index that allows us to group the data. So the horizontal one is just by design based on Cassandra, and the second one in a vertical fashion is based on secondary indexes. What are the benefits? So we were able to do geo-redundancy here across two data centers of about 40 to 45 millisecond of latency over the WAN. Additional thing is that we can dedicate certain set of machines or replica groups for performing extraction or reads only. And that way, you're not adversely impacting the ingestion performance. So two of the data centers or two of the replica groups will have just the ingestion traffic and no read or bulk extraction, whereas the other two will have bulk extraction. So you're able to segregate the load in that fashion. And also, you have the ability to do different replication factors per data center or replica group. And that also gives you a lot of flexibility in terms of the replicas or the storage that you will have to do at each group or data center. The data consolidation, of course, gives us a single view of the data in a single location, so we can ask questions and make sense out of the data without having to do extraction. We can do low latency applications. Within minutes of such an event happening, we're able to ask questions and get the data and query the database. At the same time, we're able to write batch or MapReduce queries because we have Hadoop in the read-only replica group. The other thing is that Hive is really nice about pivoting the data. So even if you have a wide row structure, in order for you to make sense out of that in the SQL realm or SQL context, you can't, it's harder to see the data if it's horizontal, but it lets you pivot the data so you can see it in a vertical fashion in almost an automatic way. So that helps as well. So what are some of the opportunities that are remaining or how we can improve such a system? there was a maxim. I mean, we always tend to think that necessity is the mother of all invention. But in this case, the business probably couldn't have thought of a near real-time pattern detection, or it didn't know about such a requirement, or didn't have one. But as we'll show in the rest of the presentation, that sometimes having a product at our disposal, knowing that such a system exists, gives us the opportunity to explore that. You know, it's like, doesn't matter, I tell my 11-year-old daughter that her cell phone is not really a necessity, but just the fact that a cell phone exists and all her friends have it becomes a necessity for her. So we'll talk about some products that will allow us to extend this infrastructure to the real-time pattern detection and response system. Also, in case of the JMS or the queuing system, which was very susceptible to any downstream failure, and additionally, failing over the entire queue from one data center to the other meant that there was a severe reduction in the capacity at the web application level, and that would have adverse impact on the experience for the end users, which is definitely not what you want to do. So that's also an opportunity that we have for improving. So what are some of the further improvements that we can do, and what sort of architecture can be laid out for performing or exacting those improvements? So I'll just turn it over to my friend Mauricio. He's going to walk you through the next iteration of this architecture.
Great. Thanks, Ameet. So before I get into talking about the architecture, I wanted to provide a little bit of context of this project. So basically what our team is doing is building a big data platform on top of Accenture's cloud platform. Now, let me talk a little bit about what the Accenture cloud platform is. From a very high level, it's a very important project to take Accenture's existing assets and deploy them as a service on demand for its clients. It's not really a cloud provider, it's a cloud broker. So it brokers between different cloud providers. But on top of this platform, we built a big data platform so that we can help take those existing assets and scale them for big data workloads. So the first iteration of this platform, we built a recommender as a service, and we had components on ETL, batch processing using Mahout. We produced targeted recommendations using collaborative filtering. The second iteration of the platform, which is what I'm going to talk about today, brings in things like distributed queuing, real-time event processing in a scalable way into the mix, as well as some of those other components. Sorry, I get parched very easily, so I will be drinking a lot of water as this goes. No Marco Rubio jokes, please. So there's a general pattern that we detected in understanding your data. And it's a process, understand, and react. It starts with processing. The architecture needs to be scalable in each component of the data pipeline, whether it's ingestion, real-time processing, batch processing, or storage. Then once we have the data inside the system, we want to understand it. I think the data discovery is still a big problem right now. There's some tools that are helping with that, Tableau, visualization tools, but I haven't seen yet a product that really completely solves this problem. But one of the ways in which to do that is to define your metadata in Hive and start querying your data so that you can understand what those distributions are and what those interesting patterns are in your data. Once you have that, then you can take some of those small samples of data and put them in R and start prototyping those analytical models. Why do we like R? Partly because we have developers who work with R. R has a great tool set for statistics. And to be honest, it's just when you're starting off in your analytical design, you want to start small, understand what the data you're using. And then once you've moved further along in the design, then you can implement that in the large scale using tools like Mahout and custom MapReduce processes. The last step in this process is taking the insights that you've learned from this and deploying them back into your real-time event processing pipeline. You can also, if you're developing predictive models, you can also put those back in using a tool like Storm and then preempt those events from happening in the first place. So one example here is, for example, have an intruder who's compromised your system, and usually there's information about how they did that through the server logs. So what you would do after that happens, you would want to ingest those server logs, understand what attack vectors they used, and then once you've gotten those insights, you can deploy them back into your real-time processing pipeline so you can alert against those events much more in real time. So the use case that we decided to tackle for this problem is around network analytics. And partly network analytics because there's an incredible growth in volume there, partly driven by more consumer devices and more video usage, and both of these are actually related because right now you can watch from an iPhone or an iPad movies from Netflix, so that puts more strain on network resources. This means that it's important to have a scalable architecture so that you can control costs. And another problem that happens is that if, for example, I'm watching a movie on Netflix and it starts buffering, usually there was like a suboptimal network event that happened before that. But if this problem occurs persistently enough, then it may force me to want to switch providers, and it basically increases customer churn for those companies. So being able to understand what those causes are, the regions that are getting affected by these network speeds, it not just helps you improve the service for those users, but it can also help you with better capacity planning for the future. So how do we go about in solving this problem? So we started off by ingesting log data for users accessing network resources, something akin to Apache web logs. We then send them to our real-time processing pipeline where we start detecting for those suboptimal network events, and we raise events when that happens. We then store them in our scalable storage. We then analyze, so again, detecting whether are these other users in that same region having the same problem, other users watching the same movie having the same problem. A lot of times it can be a particular server that they're trying to access that is very high in demand. And so we take those insights and we deploy them back into the processing pipeline. Similarly, we want to be able to visualize the data that we stored so that it gives a more intuitive sense for the operator. We're also in the process of developing some real-time notifications using things like Node.js so that when an event happens in the first place, you're notified in the UI as soon as possible. So what tools did we actually use to go ahead and deploy this? Because we're trying to keep costs down, trying to develop an as-a-service model, we wanted tools that were open source and scalable. So in the ingestion side, we are using Apache Kafka. This is a distributed queue that was developed by LinkedIn and manages their operational data pipeline. It has persistent storing. You can replay messages if something gets lost. And overall, it's very easy to use. It also works very well with Storm. I won't go too much into detail right now about Storm because I actually have a couple of other slides that dives into that, but I'll move along. Cassandra, I'm sure you all know the benefits of Cassandra: high throughput, multi-data center support, very good scalability. And plus, Big Data Stacks provides a Hadoop integration so that then we can use tools like Hadoop, Mahout, Pig, and Hive to analyze the data. We also, as I mentioned before, use R to do the prototyping. And then for the visualization, we use Liferay as our open source portal. And on top of that, we deploy HTML5 technologies like D3.js and crossfilter.js. So I'm going to dive a little bit deeper into if this clicker works. Did it run out of battery? Sorry, could we get some help here? No. It may have lost power. Uh-oh. It doesn't work from there.
You want to just go ahead and talk about the next slide?
Oh, hold on. Skipped a couple of slides here. I'm going to try to go through this a little bit faster then. So why did we choose Storm? What were our needs? First, we have a lot of multiple use cases. Storm, different from other CEP engines, not just lets you detect events, but also do transformations, computations, predictive analysis. It's scalable, as data size and velocity increases. It's also fault tolerant. So, a lot of the times we're dealing with mission critical data, so we don't want to be losing insights of that as it happens. Going back to the intruder alert, if your nodes go down, that may be exactly a time when a cyber attacker may affect your system, so you want to prevent that from happening. And then reliability. And then reliability is not just a guarantee that the messages were processed, but also the ordering of those messages were kept the same. And this is very important for time series data where you want to keep that ordering the same. Storm allows us to do this by enabling us with low-level primitives. At the end of the day, Storm, you can develop Storm with Java. It's basically custom Java logic. You can also use other languages because it's all implemented using thrift structs. So there's Python, where you can also use Python to deploy Storm topologies. And it also, through scalabilization, it gives you a multi-tier parallelization strategy. And multi-tier in the sense that you can specify for a particular topology how many worker processes are going to be run on that. But you can also, for specific bolts, and I'll go into the details of what these are later, how many threads those bolts are going to be running. And this is important because there are some bolts that may be very lightweight. You may not want to dedicate too many threads, but there are others that are more high compute intensive, which you want to dedicate more threads to. It also has robust failover strategies. Each process is under supervision. So if a process dies, it gets restarted automatically. Additionally, Nimbus, which is like a master for the Storm topology, ensures that if, for example, a worker node dies, it will redistribute those tasks the worker was processing to another worker node. And then with reliability, it guarantees that the messages are processed across the pipeline. It basically sends acknowledgements back to the spout after each bolt emits a tuple. So I'm going to talk a little bit about primitives. It starts with basically a topology. A topology encapsulates a streaming application. It's akin to a MapReduce job, except that a MapReduce job is, eventually ends, and a streaming topology only ends until you kill it. It's also basically a graph of spouts and bolts. You also have a stream, which is an unbounded sequence of tuples, where a tuple is basically the data that contains the streaming data. In our case, it's information like the IP address, a user agent, location, etc. You then have your spouts, which are your input sources. Basically, they connect with things like Kafka queue, or they can be also API, and they start reading tuples from there and start emitting it to the other bolts. And then the bolt is really the main processing unit. And the important thing about the bolt is that you want to try to keep it as small as possible, partly because it's more focused that way on that task. From a modularization perspective, you can have different bolts assigned to different tasks. We, for example, developed a sessionization bolt for this, which applies to a couple of other use cases. The other reason is because of the task parallelization. You can increase the number of threads for that particular bolt. So it's good to keep it as small as possible. And if you needed to do some complex computation, then you basically would split it up into a couple of different small bolts and just connect the graph together through the topology. So I'm going to talk about an example that illustrates this. This is the topology that we are using to detect suboptimal network speeds. And basically, it starts with, we have a Kafka spout that's reading from a Kafka topic in the queue. And it starts reading this network request data. And it goes into our pre-processing bolt, where we start filtering the data against specific event types. We parse the user agent string to retrieve device and OS information. And we retrieve timestamp information. There's a few other things as well. We then emit it to the sessionization bolt, where we establish 10-second sessions per IP address. The goal being so that we can understand the network speed for that session, but as well the network speed across all sessions for an IP address. So then we calculate the network speed for that session. Essentially, it's the content size divided by the amount of time that it took to execute that request. And we also keep an average of the network speed for that particular IP address. We also identify whether that speed was a suboptimal speed, and if so, we raise an event on it. And then finally, we store both the events and the network request data into our Cassandra database. I'm going to talk a little bit about how parallelization works in this example. So using the same topology that I was just talking about, the way in which you would parallelize the data is you would use fields grouping. So through fields grouping, you can say, for this particular IP address, always use this bolt to process it. And so this has a lot of advantages, particularly for the calculations we're doing. The other advantage with parallelism as well is that you increase your throughput. So basically guarantees that the IP address from IP1 is always processed by the bolts in the first stream, and IP address from IP2 are processed by the second stream. Another interesting topic in this area is branching and joins. So here we have two different processes. In stream 1, it's the same one, detecting the suboptimal network speed. In stream 2, it's basically a bolt that calculates the network speed for a particular location. And it uses a fields grouping on the location to ensure that it always goes to that bolt. And basically what the goal of what we're trying to do here is compare how is my user network speed compare against other users in my region. Basically what would happen here is both of them are processed in parallel, and then they're joined in the join bolt, where basically it becomes a union of both of the data fields. There's a slight cost in doing this. You have to basically wait until both streams get to the same point in order to join them, and there's a slight increase in performance or decrease in performance in joining them as well. And then once we have both of those data sets unionized, then we can compare the speeds and then store them in Cassandra as well. So another topic that I want to talk about is rule execution. So Storm is very low level. So one of the things that we wanted to try to create is how do we abstract basically like a CEP engine on top of Storm. So the first way we did this is we created custom bolts to detect these network events. But approach that we like better is basically using the rules library, which is a Java library that can be plugged in to a Storm bolt to handle that for us. The advantage there being that rules reads from a file the specific rules that you're interpreting, so you can change those rules from the file instead of having to modify your topology or modify your bolt and then redeploy that topology. The way we go ahead and do this is we basically replace the identify suboptimal speed bolt with a rules bolt. Then the other nice thing about Storm is that it integrates very well with Cassandra. So we use Hector API to store the data into Cassandra. We basically create dynamic columns with the column names being time UUIDs for the data. And then we store a JSON string with the relevant network data. So some of the lessons learned that we had from working through this. First, when you deploy a topology, you can have a lopsided situation where you, for example, if you have 5 threads and you have 8 worker processes, 8 worker processes split up between 2 servers, you can have 4 of those threads running on one server and the other thread running on the second server. So to do this, you can rebalance the topology, and now, as of the latest version of Storm, you can go to the UI, and it's a point-and-click process, very simple. The other thing is tweaking the parallelism for the bolt, because you can set the number of threads for specific tasks. It's an exercise in figuring out what's the best optimization to do there. The other nice thing is that you can isolate topology. So if you have a topology that's more higher priority than another one, you can isolate that topology in a different set of servers than the lower priority topology. The other thing is if you want to use time UIDs, I recommend to use the time UID utils. You want to use UIDs of type 1 to store that. So that library makes it very easy to do. And then finally, by default, Storm has its log4j level set to info. The problem here is that for every bolt that gets emitted, it basically writes it to the log file. So this can quickly increase the size of that. And particularly for, like in our situation, we have our root partition is not very big. We have additional partitions. It can very quickly run out of space. So you want to make sure that you disable that or put it to debug. Some of the next steps that we're working on right now are the use of Trident. Trident is a high-level language on top of Storm. So instead of going to your Storm topologies, you would have a language that's more similar to SQL to define those processes. The other thing is that right now we have the rules defined in a file. We want to be able to externalize those rules and store them in a Cassandra column family, just because it's going to be easier to modify there from the UI. We're also developing the predictive models, as I mentioned earlier, so that we can preempt those network events from happening by determining which fields in particular are mostly predicting the dependent variable, which in this case is network speed. And then the real-time notifications, so when you send the event, being able to display it immediately in the dashboard. So that's it. Any questions? They guarantee that, sorry? Yep. After each bolt emits a tuple, it sends an acknowledgement to the spout. And basically, unless, if it's an acknowledgement or a fail, if it's a fail, then it will replay the spout, the tuple again from the original data source, in this case, Kafka. So for each part of that process, it has to send an acknowledgement. It has, you mean the acknowledgement or?
You can think of the entire system as an ESB or a bus itself.
Yeah.
When you think of Storm, it is sort of kind of mimicking that concept.
Each bolt, there's like the base bolt basically implements that automatically for you. So it's not something that you have to explicitly set. As an input source, you mean? So that's where the spouts come in. There's multiple different spouts that are available as part of Storm. I would recommend checking the website. I also glossed through a lot of the architecture details. I definitely recommend checking out Nathan Mar's GitHub page. It goes a lot deeper into that and includes some of those available spouts. But if not, it's still Java logic, so you may be able to hand roll it yourself.
So at the start, you had mentioned that one of the problems with the initial architecture was the loss of messages and the failover issue. Was that solved mostly by going to Kafka instead of a JMS queue, or was there some part in Cassandra that also assisted in making that more robust?
Well, that problem was actually related primarily to the transient database, the storage, which was getting the information from the queue and then storing it in that database, which was a standard traditional RDBMS system. Since that system was not able to keep up with the incoming volume, the messages were backing up, and that was leading to that problem because of the downstream issues. So once we replaced that with Cassandra, we're able to tackle that issue to a large extent. What we're saying is that even after that, there are still some opportunities that remain in terms of having a distributed structure. And especially with Kafka, you have the ability to do mirroring from two different sites into a single site. So you can get the messages from multiple locations into a single place and I wouldn't say completely eliminate, but solve that problem to a large extent.
So you have a real-time compute engine pipeline, Where were the latencies? Where were the performance issues? And kind of how did you resolve those?
Well, so that's still something that we're working through right now. We're still doing the process performance testing. So the work that we're doing right now is still in development. So yeah, can't go. We don't have those numbers yet. Not yet, because we haven't. Yeah, we. So that was part of the. Yeah, I wouldn't say that we detected any other bottlenecks right now. So.
The other areas where you could face problems is that if you're trying to use some machine learning algorithm, like he pointed out, where let's say that you created a model in R and then you want to inject that model into the topology. If the model is complex enough, then that could add to the delay. And especially one of the slides that he pointed out was you are joining two different streams. And if one of the streams is relying on a machine learning-based model, then that's going to adversely affect the other stream coming in. And any sort of operations that depend on such an action, you're going to inject some delay. All right. Well, thank you very much.
Thank you.
Yeah.